The objective of today's module is we are going to derive conservation of mass, and in subsequent modules we are going to derive conservation of momentum and then we would be deriving conservation of energy. So, this is our broader objective. For today's module, let us take up conservation of mass. So, the conservation of mass, let me just write down conservation of mass. We also call generally this as continuity equation. Continuity equation. Okay. So, to derive this, we are going to employ Reynolds transport theorem. Okay. So, what is Reynolds transport theorem? We have been taught in the previous modules what is Reynolds transport theorem. I will just state the equation which we are going to use, that is Reynolds transport theorem. That is dB system divided by dt, please note that this is total derivative, is equal to dou by dou t of rho b dV Cv plus integral of Cs rho b v dot n dA. Note that rho is density, dV is the elemental volume, and what is b? Here v is velocity vector, n is the outward normal vector. So, b is equal to 1 for conservation of mass. Just let me tell you what would happen for B in case of momentum and energy also, just for the sake of it. B equal to velocity in case of conservation of momentum. And B would be equal to energy in case of conservation of energy. So, what is B? Capital B. Capital B is equal to m into small b. Okay. So, this is what, and for our moment, that is for continuity equation of the conservation of mass, we are going to get small b is equal to 1. So, let us substitute this in this equation 1. So, what would I get? dm system divided by dt is equal to dou by dou t of rho dV of Cv. What is Cv? Cv is standing for control volume. Cv is standing for control volume plus Cs rho V dot n dA. Cs is for control surface, that is the mass flow rate flowing through the control surface, that is this term. So, now let us see what does this equation become. So, that is, let me rewrite that again, dm system divided by dt is equal to dou by dou t of rho dV plus rho V dot n dA, rho V dot n dA. Okay. So, now let me just take, before we take the control volume, what do we state the conservation of mass for a system? Conservation for a mass for a system, we say that mass is conserved. That means mass is not created. So that means dm system by dt would become 0. Now let us take a small elemental volume. And this elemental volume is having dimensions delta x, delta y, delta z. And let me remind you, these are the directions, that is x, y, z, and the velocity in the x direction is u, velocity in the y direction is v, velocity in the z direction is w. Okay. Now, what is this term? So, the first term of this equation 1 would be, this is 2, let us call this as 2 because we have already called 1. So, the first term, that is dou by dou t of Cv rho dV would be equal to del rho by del t delta x delta y delta z. Correct? Now, let us try to find rho v dot n dA, rho v dot n dA. Okay. So, now what is the mass flow rate which is getting in the x direction? What is the mass flow rate which is getting in? Rho, velocity is u, and the area of the x plane is delta y delta z. Now, what is it is getting out? So, getting out, to get that we have to invoke the Taylor series expansion. So, what does Taylor series expansion say? It says that f of x plus delta x equal to f of x plus del f by del of f of x upon del x delta x plus 1 by 2 factorial del squared f of x upon del x squared delta x squared plus all higher order terms. Now, generally we neglect the second order terms, we take only the first order terms. So, what would happen here for us? It would be rho u delta y delta z plus del by del x of rho u delta x delta y delta z. So, this is in the x direction. Now, let us take up y direction. So, you have rho v, the area is delta x delta z, and what is getting out would be rho v delta x delta z plus del of rho v upon del y delta y delta x delta z. So, we completed the velocity in the y direction. So, what is left out is flow rate in the z direction. So, that if I draw this way for the area delta x delta y, so what would I get? Rho w delta x delta y, rho w delta x delta y, and what is getting out would be rho w delta x delta y plus del of rho w upon del z delta x delta y. So, now what is this? Let us get back with this control volume thing. Let us get back to this rho v dot n dA control surface. That is, what is the mass flow rate getting in and getting out across all the surfaces of the control volume is what we are keeping, we are bookkeeping. Now, whatever gets into the control volume is always negative. Why? For example, let us just take rho u delta y delta z. What is the velocity direction of u? It is from left to right u, correct. But what is the normal vector, outward normal vector to the x plane, to this plane? It would be from right to left. So this is the normal vector. What is the angle between u and n now? Theta is 180. We know v dot n is u n cos theta, unit vector. So it is u cos theta. So that is u cos 180. Cos 180 is minus 1. So you get minus. So that's why always mass flow inlet is negative. Now let us take up outward. So what would happen for outward? Velocity u and outward normal vector is also from left to right. So you have theta equal to 0. So you have u cos theta as u cos 0, that is plus u. So now let us make this generalization, and we are going to use this again and again. So I will not put every time cos theta 180. So always inlet, that is whatever is flowing into the control volume, is going to be negative. Whatever is flowing out of the control volume is going to be positive. Let us remember this, because we have understood how we have got on that. So if we do this, so I get del by del t of Cv rho dV equal to Cs rho v dot n dA equal to, so whatever is getting in would be minus rho u delta y delta z, getting out in the x direction is plus rho u delta y delta z plus del of rho u upon del x delta x delta y delta z. Okay. Then in the y direction you have minus of rho v delta x delta z plus rho v delta x delta z plus del of rho v upon del y upon del y delta y delta x delta z minus rho w, that is in the z direction, rho w delta x delta y plus getting out is rho w delta x delta y plus del of rho w upon del z delta z delta x delta y. As you can see here, this term gets cancelled with this term, and this y direction, this term gets cancelled with this one term, and this term will get cancelled with this term. So what am I left out with? So I am left out with rho v dot n dA is equal to del of rho u by del x plus del of rho v by del y plus del of rho w by del z, and please notice that I have taken delta x, delta y, delta z common. Now let us substitute all these terms in my equation 2, that is dm system by dt equal to dou by dou t of rho dv of Cv plus rho v dot n dA. We have found each of these terms. So dm system by dt is 0, we have just found, and we wrote this first term on the right hand side as del rho by del t delta x delta y delta z plus this rho v dot n dA is just on the top. So you have del of rho u by del x plus del of rho v by del y plus del of rho w by del z delta x delta y delta z. So if I can just throw out this delta x delta y delta z, because left hand side is 0, so I have del rho by del t plus del of rho u by del x plus del of rho v by del y plus del of rho w by del z is equal to 0. This is actually the conservation of mass, but in this form we generally don't remember or use it. But I would like you to remember this because we would be using this form of the equation while we derive conservation of momentum. Okay, so I would request you to remember this equation in this form so that I will be invoking this equation again when we go for conservation of momentum. Now let us do the algebra for this. So del rho by del t plus, now I have to just differentiate this. So what will I do is, I will first take u del rho by del x plus rho del u by del x. So first I kept u constant and differentiated rho. Now here I have kept rho constant and differentiated u. Let us do this for next two terms, that is v del rho by del y plus rho del v by del y plus w del rho by del z plus rho del w by del z is equal to 0. Okay. So now let us take, so what is this whole of this? Whole of this is nothing but my total derivative of my density. So I can write that as d rho by dt plus rho of del u by del x plus del v by del y plus del w by del z is equal to 0. So what did I get? D rho by dt plus rho of del u by del x plus del v by del y plus del w by del z is equal to 0. So people also remember this as d rho by dt plus vectorially if I just write rho of del dot v equal to 0. Du by dx, correct. Okay. So now you see here I should visualize like this. If you remember our earlier modules, del u by del x is the stretching in the x direction, del v by del y is the stretching in the y direction, del w by del z is the stretching or the linear deformation in the z direction. So del dot v is the net dilation rate, that is net how much it is getting dilated, dilation rate. If this is the general equation, but what does this equation reduce to in case of incompressible fluids? In case of incompressible fluids, my d rho by dt term is 0 because density is neither varying with time nor with space. So what will I get? Del u by del x plus del v by del y plus del w by del z equal to 0. In fact, if you recollect, this is what we had derived as net dilation in the previous modules, net dilation rate. So for incompressible fluids, net change in the volume is 0. There can be stretching in positive direction in the x direction, but it can get compensated with the stretching in the negative direction in the y direction. So that way net dilation rate will be 0 for incompressible fluids. So this is so much about for the conservation of mass. Now let us take up conservation of momentum. So let's start with conservation of momentum. So I would like you to just see this slide for a minute. If you just shift to slides, so you have same, we are going to write same Reynolds transport theorem. By Reynolds transport theorem, conservation of momentum. So let's get back to our writing. So that is by Reynolds transport theorem. I will not write Reynolds transport theorem, I will just write RTT. By RTT, so we have del by del T of CV rho B dV plus rho B V dot N dA is equal to sigma of d of B system by dt. Now, but for conservation of momentum we said that B is equal to velocity, correct. So, that is velocity. So, you have dou by dou T of CV rho V dV plus V rho V dot N dA is equal to, if you recollect our conservation of momentum for system, we say that the net rate of change of momentum is equal to sum of the forces acting. So, that is sigma of F of CV, that is the forces acting on the control volume. So, this is our mother equation which we are going to build upon. Okay. Just I want to, before we derive this rho V dV and V rho V dot N dA, I just want to tell you that what are the forces which are acting. There are two types of the forces which are acting. One is surface forces, so another one is body forces. As the name itself suggests, surface forces are the forces acting on the area, body forces are the forces acting on the whole body. So, what are the surface forces? They are the forces acting because of pressure, because of normal stress, because of viscous stress. Okay. Viscous stress can also be called as shear stress. And body forces can be plenty, we will just name a few. Generally gravity force, then Coriolis force, then centrifugal force. So, now with these forces, let us take this mother equation which we shall call as Roman number 1. Let us take up this equation and build upon each term by taking a elemental control volume. So, let's write the first term, that is dou by dou T of rho V dV CV equal to. Okay. So, this is nothing but you have. So, to remind you, there are going to be three momentum equations. What are those? In three directions: x momentum, y momentum and z momentum. We shall derive x and write in the same lines we are going to write directly for y and z. So, if I take x momentum equation, so I get velocity, I should be taking only u. So, del of rho u by del t, and volume of the elemental volume is delta x, delta y, delta z. Okay. So, that is my first term of the equation 1. So, now let me take up the V rho V dot N dA. This is the momentum, that is velocity into mass flow rate, rho V dot N dA. So, the momentum in the x direction, remember we are in the x momentum. So, let us draw the elemental volume. It is a parallelepiped whose dimensions are delta x, delta y, delta z. Okay. Now, just reminder, that is, you have u, v, w in the x, y, z direction. Okay. So, the momentum in the x direction is velocity u into the mass flow rate in the x direction. So, what is the mass flow rate in the x direction? Rho, velocity u, area in the x plane is delta y, delta z, delta y, delta z. So, what is getting out? So, same, rho u squared delta y delta z. Again I am going to use Taylor series expansion. I am not going to write that equation. I am going to take only first order term. So, you get del of rho u squared upon del x delta y delta z. Here we need to pause for the y direction. What is the flow rate in the y direction? This is where students get confused. This is where I generally pause and ask them, what is that we should write here? This is the key for this derivation actually. So, mass flow rate in the y direction, there is no confusion. Everyone would say rho v delta x delta z. I generally ask in the class, what should I put here? U or v? Most of the times, most of the students say v. But remember, what is that we are bookkeeping? We are bookkeeping the momentum in the x direction. So, mass flow rate is in the y direction. It is like a jet going from bottom to top. But how much that jet gets deflected because of the velocity in the x direction? Because that is the one which is going to contribute for the x momentum. So, that is why it is going to be u into rho v delta x delta z. Done. If this is done, the whole derivation is over, because this is the key in this derivation. So, please alert to the students. You can when you are teaching, you just take a pause, ask the students here and say that whether I should take u or v, and explain them why we are taking u, because we are bookkeeping the momentum in the x direction. So, what is getting out is rho uv delta x delta z plus of del of rho uv upon del y delta x delta z. Similarly, for w, same thing. Flow rate in the z direction is rho w delta x delta y. What is the momentum we are bookkeeping? X, that is u. So, what is getting out is rho u w delta x delta y. Here it is getting little clumsy, bear with me for that, plus del of rho u w upon del z delta x delta y. Okay. Just to remind you, whatever gets in is always going to be negative, whatever gets out is going to be positive, correct? So, if I do that, so v rho v dot n dA in the x direction is rho u square delta y delta z, which is entering, plus, that is minus. What is getting out is plus rho u squared delta y delta z plus del of rho u squared upon del x delta y delta z. Okay. So, now next term is minus rho u v delta x delta z plus rho u v delta x delta z plus del of rho u v upon del y delta x del z. So, the last terms are minus rho u w delta x delta y plus rho u w delta x delta y plus del of rho u w upon del z delta z, delta x, delta y. So, we will, for this module we need to simplify this. For now, for this module we will stop here and continue this in the next module to converge about this left hand side of our momentum equation. Okay.